It was a quiet Saturday morning, June 1st, 1974. The sort of calm that almost dares you to forget how quickly silence can shatter. At the Flixborough chemical plant in North Lincolnshire, England, a 2-year-old caprolactam unit, meant to be the pride of the site, was being brought back online. It hadn't been much of a success. From the start, the unit had been plagued with production problems, leaks, and setbacks. It had only reached full output earlier that year, and just days ago, it was shut down again due to yet another suspected leak. But no one could have guessed what that ordinary Saturday would become. By late afternoon, the plant would be gone, blown off the map in a cataclysmic explosion. The blast would be felt up to 50 kilometers away. Lives would be lost. Homes damaged. Families devastated. And a hole would be torn, not just into the earth, but into the conscience of an entire industry. My name is NJ, and this is Freak Files. And today, we step into the haunting ruins of the Flixborough disaster. Flixborough is a small, unassuming village. Quiet. Pastoral. The kind of place you'd pass through without noticing, except, half a mile from its center, something far more volatile had moved in. Back in 1938, a new neighbor arrived, Nitrogen Fertilizers Limited. Over time, the company evolved. In 1964, it merged with Dutch State Mines to form a new entity, Nipro Limited. And with it came change, not just in name, but in ambition. The plant shifted from fertilizer to something far more complex, caprolactam, a crucial ingredient in manufacturing nylon. A first unit went live in 1967 using phenol hydrogenation. But soon, they wanted more. More production. More output. More risk. In 1972, a new installation was built. Dubbed Phase 2, it used a chain of 6 massive reactors to oxidize cyclohexane, a process both precise and unforgiving. Each reactor sat slightly lower than the next, using gravity to move the chemical slurry forward. Inside, cyclohexane was pressurized to 8.8 bar and heated to 155 degrees Celsius. Compressed air, catalysts, safety valves, heat exchangers, flares, it was a symphony of chemical engineering. Except the music was off-key. Almost immediately, the installation struggled. Technical issues. Disappointing yields. Persistent leaks. One of those leaks would spark a decision that changed everything. March 28, 1974. Another leak was found, this time near Reactor 5. By evening, a crack in the steel wall was confirmed. The next morning, the full extent came to light, a 6-foot gash stared back at engineers like a wound no one wanted to own. Shutting the system down was the only choice. But without Reactor 5, the whole chain was useless. That's when a different idea emerged. Instead of waiting for a proper replacement, management decided to bypass Reactor 5 entirely. The plan? Build a custom pipe to link Reactor 4 directly to Reactor 6 using whatever parts they had on hand. No design consultation. No detailed modeling. Just a team of engineers and welders on the workshop floor, cutting and welding what would become known as the dog-leg pipe. They used 20-inch diameter pipe, smaller than the original, and connected it using bellows and welded extensions. The geometry wasn't ideal. The inlet and outlet were at mismatched heights. But it fit. And it passed pressure testing. Sort of. The system was tested with nitrogen up to 9 kilograms per square centimeter. But British standards required hydrostatic testing at a pressure of at least 11 kilograms per square centimeter, the same pressure at which the safety valves were set to blow. That final, critical step? Skipped. On April 1st, the plant resumed operation. Through April and May, the plant ran almost continuously. The makeshift bypass held. There were shutdowns, minor repairs, minor pressure issues, but nothing that raised alarms. Until May 29th. Another leak. More shutdowns. The system was cooled, patched, and tested again. On May 31st, early in the morning, startup began once more. But it wasn't smooth. Reactor pressure spiked. Leaks appeared, then seemed to vanish again on their own. Heat rose too quickly, then too slowly. Technicians wrestled with stubborn valves and outdated gauges. And the tools they needed most. Locked away, inaccessible. Still, they got the green light to restart. The next day, June 1st, the bypass pipe would face its greatest test. It was 7 a.m. on Saturday, June 1st, 1974. A fresh shift clocked in, unaware they were stepping into a ticking time bomb. The plant was unsettled, rumors of leaks, strange pressure readings, inconsistent startup procedures. Even the official inquiry later admitted the evidence regarding the shift's commencement is unsatisfactory. No one could say for sure what state the system was truly in. By 8 a.m., pressure in the system had climbed to 8.5 kilograms per square centimeter, still within limits, but troubling. Then, reports trickled in of a high-pressure event that had required venting. It passed, mostly unnoticed. No leaks were formally reported. At 9:30 a.m., the operators introduced steam into the heat exchanger, intending to raise the temperature to the critical 160 degrees Celsius mark. But something wasn't right. By noon, a control technician noticed the pressure climbing, too high, too fast. The steam was reduced, but the pressure didn't budge. It kept climbing. Eventually, an operator was sent to manually open a block valve. That did the trick. The pressure dropped back under 8.8. But now, the temperature had fallen below operating minimums. The chemical reaction wouldn't start in these conditions. And the team faced a grim catch-22, you either raise the temperature and risk overpressure, or stay cold and stall the entire system. At some point, likely out of desperation, the steam bypass line was opened, either officially or by habit. We'll never know for sure. But if it was, that decision would mean the difference between frustration and catastrophe. What had begun as just another rough startup was becoming a game of chemical roulette. No one knew where the bullet was. But they were pulling the trigger. Late in the afternoon, the makeshift bypass, built with mismatched parts and tested below safety thresholds, finally failed. At 4:51 p.m., the 20-inch pipe ruptured at its bellows. In an instant, over 60 tons of cyclohexane were released into the air, pressurized, flammable, and already hot. The chemical cloud surged outward. It made contact with the hydrogen reforming tower nearby, an ignition source waiting patiently for the worst to happen. It didn't wait long. 4:53 p.m., the entire Flixborough chemical plant detonated in a colossal fireball that lit the sky and cracked the earth. The explosion could be felt up to 50 kilometers away. Windows shattered in towns no one had even connected to the plant. Roads warped. Buildings folded like cardboard. Flames erupted across the site, some reaching 100 meters high. The control room, the heart of the entire operation, was obliterated. 18 staff members inside were killed instantly. In total, 28 people died. 36 were injured on site, and over 50 more were injured off-site by flying debris, fire, or collapsed buildings. It was a weekend, which likely saved hundreds. On a normal weekday, over 500 workers would have been on the premises. More than 2,000 buildings in the surrounding area were damaged. Fire crews battled the blaze for more than 2 days. The disaster had unfolded in minutes, but its consequences would last for decades. The investigation began quickly, but faced a devastating problem. Most of the evidence had been vaporized in the explosion. Critical records, operating logs, eyewitness testimonies, all gone. Investigators had to rebuild the story from the fragments that remained. But one truth became obvious early. The disaster began with the removal of Reactor 5 and the decision to use a homemade bypass pipe in its place. The design hadn't just been subpar, it was non-compliant. The welds weren't inspected to code. The geometry was flawed. The pressure tests fell short of the standards. And worst of all, no one consulted the manufacturer of the bellows used in the pipe. Had they done so, they would have seen a warning in the manual, clear as day, these bellows were not suitable for this application. For a month, that pipe had endured repeated pressurization and depressurization cycles. Metal fatigues. Welds weaken. And then it snaps. It didn't matter that the operators had followed protocols that day. It didn't matter that the welders had built exactly what they were told. Because the system itself was broken by management decisions, cost-cutting, and a climate of quiet desperation. At the heart of it all was one of the oldest forces in the world, money. Britain in the 1970s was a mess. The country was in the grip of a miners' strike. The government declared a state of emergency. Factories were limited to 3 days of electricity per week. Nipro was bleeding money. The caprolactam unit had never reached its projected output. It was a 2-year-old investment already looking like a failure. They couldn't afford another shutdown. So the agitators, vital safety components, were turned off to conserve energy. The bypass was installed quickly to minimize downtime. Safety testing was limited. Engineers weren't consulted. The pressure, both literal and financial, was immense. And it pushed the company to cut corners that would cut lives. In the aftermath, over 6,000 public liability claims were filed, costing around £24 million, roughly £150 million today. A few years later, another chemical disaster would strike, this time in Seveso, Italy. Together, the Flixborough and Seveso events pushed the European Union to create new laws, the Seveso Directive, passed in 1982, which drastically improved industrial safety protocols across Europe. Incredibly, the Flixborough plant was rebuilt. It reopened despite protests. But Nipro would never be the same. The investigation cleared the operators and welders of blame. They were working with what they had. The real responsibility lay higher up, with those who authorized a system they didn't fully understand in a desperate attempt to meet production quotas and salvage profits. They thought they could make it work. They thought they could manage the risk. They thought wrong. What if they had waited just a little longer? What if they had simply shut everything down, investigated Reactor 5 properly, and done the rebuild by the book? Would anyone have died? We'll never know. But in that uncertainty lies the lesson. Because Flixborough wasn't just a chemical accident. It was a human one. If you found this story as haunting and important as I did, consider giving it a like. It tells the algorithm this isn't just another video. And if you've got thoughts on who should have taken responsibility or how this disaster could have been avoided, leave a comment. I read every one. It's free. But it supports the channel more than you think. This is Freak Files. Goodbye for now. Until next time.